When you sit down and chat with an AI and it just spits out this perfectly crafted poem, or maybe it solves a super complex coding problem in literally seconds, it really feels like magic, doesn't it? I mean, it kind of feels like there's this tiny conscious brain living right there inside your screen. But today, we're going to absolutely shatter that illusion, because underneath all that seemingly intelligent poetry and conversational charm, yeah, it's not magic at all. It is just massive, mind-bogglingly fast mathematical operations. Welcome to this explainer. Today, we're taking a journey to demystify the black box of artificial intelligence by looking directly into the engine that powers the whole shebang. So, here's our roadmap for today. We'll start with exactly why AI needs math, move into vectors, scale things up to matrices, look at the math of neural networks, explore the matrix bottleneck, and finally, we'll reveal the secret inside GPT. Let's get into it. Okay, let's dive into this. Section 1. Why AI needs math. Let's start shattering that black box illusion right out of the gate. I want to pose this first core question directly to you. Why does AI actually need math? Because, we usually think of computer science as writing logic, right? If-then statements, loops, hard-coded rules. But modern machine learning, it doesn't use pre-programmed logic to understand the world. So how does a computer actually ingest, process, and learn from a messy, completely discrete reality? Well, as developers and practitioners across coding communities constantly point out, linear algebra is the absolute undisputed foundation of all machine learning. You simply cannot represent data without it, period. Every single image, every word you type, every sound bite, it's all represented mathematically. And then, once you actually have that data, you need calculus to optimize your cost functions. That's what helps your model learn by tweaking variables. Honestly, without linear algebra and calculus, you wouldn't even be able to debug a model when the gradients stop flowing properly. You absolutely have to know what's happening under the hood when you hit train. Moving right along to Section 2, Vectors, the AI molecule. Shifting away from the macro concept of math for a second, we arrive at our second major question. Why are vectors absolutely everywhere in machine learning? I mean, if you read any paper or look at any code base, it is literally just vectors on top of vectors. But why? How does real-world discrete data, like, say, a paragraph of text or a picture of your cat, actually get swallowed by a computer? The answer, my friends, is the vector. You can think of a vector as the core molecule of AI. By definition, it's really simply a sequence of numbers, but what it actually does is encode discrete, real-world data into a continuous mathematical space. Think of it like this. If you have 3 numbers, that data lives in a 3D space. If you have 10 numbers, it's a 10D space. It's the perfect translator, taking our messy physical world and turning it into distinct arrays of numbers that a computer natively understands. So the crucial point here is that by putting data into this continuous vector space, we unlock some incredible geometric advantages. Because the space is continuous, we can use calculus, specifically gradient descent, to smoothly train our models. But what's even cooler? It's how we measure similarity. In a vector space, mathematical distance actually measures similarity. If 2 images are similar, their vectors will literally be plotted close to one another in that space. And it turns out, this geometric proximity captures true semantic meaning. Just look at this classic example from the famous word-to-vec model, which embeds words into a vector space. Because vectors capture real meaning, you can actually do math on concepts. No, really. If you take the mathematical vector for the word king, subtract the vector for man, and then add the vector for woman, you land almost exactly on the vector for queen. That is mind-blowing, right? We aren't just processing raw data here, we are mathematically computing human semantics. Which brings us to Section 3, Matrices, the computation engine. Now that we've got our molecules, we obviously need a way to process them. So here's our third core question. Why are matrices everywhere? If a single vector can hold the meaning of a word or an image, why do we even need matrices? Well, think about it. What happens when an engineer needs to handle transforming thousands or even millions of these vectors at the exact same time? Enter the matrix. A matrix is essentially just a grid of numbers. It's used to organize all those individual vectors so we can perform massive batch transformations on them simultaneously. If the vector is the molecule, the matrix is the computation engine. It acts as the ultimate matchmaker between the input data you feed into the model and the learned weights that the model has memorized over time. And the core operation happening inside this engine, that's called the dot product. Think of it kind of like a massive factory. The rows of one matrix are your customers, coming in with specific raw material requests. The columns of another matrix are the factory's product recipes. The dot product is this mathematical chemical reaction that measures the exact compatibility between the two. It computes precisely how well your input features match the model's learned patterns to calculate crazy fast, accurate predictions. Let's keep building. Section 4, Math of a Neural Network. Okay, so we have our vectors and we have our matrices to process them. This naturally brings us to our final core question for this explainer. What is a neural network mathematically? We hear about nodes, hidden layers, and deep learning all the time, but stripped of all those flashy biological metaphors, what is literally happening to the numbers? To really understand this, we have to look at the difference between early AI and modern AI. Early models used these things called binary perceptrons. They basically just spit out a 0 or a 1. And because of that, they were incredibly brittle. Like a tiny update to the weights could wildly flip the output, which made learning virtually impossible. Modern neural networks completely fix this by using smooth, continuous activation functions, like sigmoid or ReLU. This ensures that a tiny incremental change in the math creates a proportionally small change in the output, and that smooth change is strictly required for a network to actually learn over time. Let's move to the next step and see how this builds into the actual mathematical process of a single artificial neuron. Honestly, it's just 3 steps. Step 1, compute the weighted sum. Basically, multiply your inputs by their weights and add a bias. Step 2, pass that raw sum through your nonlinear activation function to smooth it out. Step 3, pass that resulting number to the next layer. And that's it. That is a neuron. Next up, Section 5, the matrix multiplication bottleneck. Now, if you scale that simple 3-step process up from a single node to billions of nodes, you realize something pretty crazy. Over 90% of the floating point operations in major AI models are dedicated solely to matrix multiplication. It's the absolute bottleneck of deep learning. When an AI generates an incredibly detailed image or writes a 10-page essay, almost all of the computing power, the electricity, the time, it's just grids of numbers being multiplied and added together over and over again. And because this happens at such an unimaginable scale, engineers have to follow the shape collapse principle. Visually, just imagine a 2x3 matrix multiplying a 3x2 matrix. Step 1, the inner dimensions, those 3's, they have to perfectly match. Step 2, as the dot product occurs, those matrices collide, and the inner 3's mathematically annihilate each other. Poof, gone. Step 3, only the outer dimensions, the 2's, survive to dictate the final shape, leaving us a brand new 2x2 matrix. Understanding this geometric collapse is absolutely vital to building AI. And this brilliantly illustrates how high-level code translates straight to geometry. When an engineer types a simple command like torch.matab in PyTorch, they're issuing a single API call that triggers literally millions of those beautiful arcing dot products deep inside the GPU. Rows are diving into columns, multiplying element by element, and collapsing shapes millions of times a second just to push that data forward. Which brings us to our final stop. Section 6, the secret inside GPT. Finally, we reach the climax of our abstraction ladder. When you take these matrices and stack them into deep, hidden layers, the network starts learning hierarchical representations. Low-level features combine into much more abstract concepts. When the model makes a mistake, an algorithm called backpropagation flows in reverse, systematically assigning exact mathematical blame to specific weights so they can adjust and do better next time. And when you do this at massive scale, we're talking billions of parameters, something incredible happens. The math actually begins to simulate compositional reasoning. Now, what's really interesting about this, and truly profound about this whole thing, is the absolute simplicity of the conclusion. At the end of the day, despite the seemingly human-like intelligence of tools like ChatGPT, it all boils down to this. Everything inside GPT is just matrix multiplication. It is just linear algebra. Billions of vectors colliding in continuous space, perfectly guided by calculus. It leaves you with a pretty provocative thought, doesn't it? If pure simple matrix multiplication at a large enough scale can perfectly mimic human reasoning, what exactly does that say about how our own brains work? Something to chew on. Keep learning, and I'll see you in the next explainer.